TTT will be given by Hannes.
Yes.
And the title of the presentation is an industrial strength audio search algorithm. Specifically, the algorithm used by Shazam. Very good. So the stage is yours.
Thank you. First, I have to point out that there's Radu. Sorry, you brought cookies because of your birthday.
Yeah. So please have some cookies. Thanks.
Bogdan, sorry. All right. So let me start. Hope you've all read the paper. If not, then I will explain. Yeah, this is about audio search, and you would wonder why on earth I'm suddenly interested in audio search. And that's a very good question. And the reason for that is that we have a project proposal with partners from industry which is about detecting mineral compositions using spectrographs. And that is actually quite related to the problem of audio search, as we will see in a bit. And this is why I looked a bit, okay, so what are like the efficient ways of getting anything meaningful out of a spectrogram? And this was one of the papers that popped up. So this is by Avery, Li-Chun, Wang, and this is actually refers to as inspiration to an earlier paper, a highly robust audio fingerprinting system that comes from the Netherlands, from Philips Research. I don't know if anybody has a...
When Philips Research Lab was still alive.
Is it not anymore? I don't know anything about Philips.
Well, Philips Research is not Philips Research anymore as it was in the 90s.
Right, so this was in 2002. But actually, I hate to say this for Philips people, this guy came up with a way better solution in my opinion. All right, so first of all, who does not know Shazam? Anybody does not know Shazam? You know, okay. For Niels,
I'm not using this graph.
For Niels, we're gonna do a demo, and also because I think it's nice to see. So basically, I have here this app on my phone, and then what it does, it listens to your microphone and detects whatever music is playing there. Niels, I'm doing this for you, so you have to pay attention. So if I play music, for example.
It's for Locket, of course.
No, I have this as one of my examples, but 1 second. They change this all the time and never understand it anymore. Wait. There we go. So if I were to play music, and then I push this button, and it immediately says, aha, this is this particular music. And it's always been a bit of a magic thing box for me, because it doesn't only do this for Johnny Be Good, which is actually one of the most popular songs, but if I were to go to, for example, Jauchzit frohlocket, to make Benno happy,
Not just Benno.
and short, which is actually a bit more complicated, because this is not only a song but also a recording. So if I run this again, it takes a bit longer. Right, and now I just found it, and it didn't only detect that this is indeed the Christmas oratorio, but this is the recording by the Thomaner Chor Leipzig, which is quite impressive if you think about it, because the classical music people, they love to replicate each other quite excessively, and if the thing is then able to exactly pin down which recording that is, not only which track that is, then that's quite impressive. All right, yeah. So how does this work? This is what the paper is about. How does this work?
So Niels, are you now installing the app?
No.
It asks for your location, so you must love it. So what is the task? Well, the task is audio fingerprinting, essentially. So if we have given an arbitrary audio snippet, find out where this is from. So we always have some sort of library of known music tracks, for example. And then we have these snippets that we don't know where they're from, and then the algorithm will find out best matching. And this is done for the Shazam app, but it's also used by YouTube, for example, to detect whether the music that some kid has put into their YouTube video is copyright protected by somebody and then gives that person money. So that's also what this kind of stuff is used for.
So they offer it as a service?
No, they do this internally. So they will give actually part of the revenue from that video to the people who hold the copyright on the music that is used in that video. Yeah, or block it if they don't have, there's also music that you cannot put on YouTube. I think we found this out with the Hypoparser paper where we had Michael Jackson and it got shut down.
Yeah.
So this is also, they also use this, for example, for radio airplay to measure, which songs are played, because they just listen to it and run these algorithms. Quite simple. Bing! This wasn't detected. Okay, here are some wonderful 90s slides that I pulled from the original author of this paper that explains a bit the constraints here, because this is of course complicated because we are basically running sound through this microphone of whatever phone you have, and then we try to get something meaningful out of it. But this is only, the second problem. The first problem is that, of course, we also might have a crappy source to play with. So here we have the problem with the imperfect source material. So compression, I think, is one of the biggest problem here that, we've passed this audio through a very high compression, then it gets like a ringtone, and then it gets very bad quality. Physical media defects is not really a thing anymore, I think. That was like in the past when we had, these turning things. Sorry. Vinyl, that's
maybe
it.
the audio source is traveling away from you.
That Doppler effect, yes, you could have Doppler effects. Tapes, of course, are also if you walked along the particle accelerator with your audio tape in the pocket, then it might also be influenced. Then you have the equipment, okay, the turntable. As I said, this is not so much a problem anymore because stuff is played from computers. But okay, I have push speakers. That is a problem. Like imagine shitty car speakers. Then this goes through the air, which means there is noise. There's echoes, all these things. So this is kind of messing up the signal. And then we have the constraints on the receiver side, which is, okay, whatever shitty microphone you have in your phone is gonna be what detects this. This is cool, they designed this system to work differently. Now Shazam works with this app, right? So it just, records and sends the thing into the cloud. But it used to work that you would call a phone number, and then you would, hold up your phone, and much like in Back to the Future, and you will hold up your phone, and it would record, and then would tell you what the song was. But if you think about audio codecs that are used in phone systems, those are the shittiest possible codecs in the world, right? I mean, they try to really cram the signal down to 8 kilohertz. It's like, okay. Noise suppression also great. If you have a noise suppression on your signal, then you lose half the signal. You have experienced this before when you ever were calling like a hotline of some company, and they play music through the phone to you while you wait, and then you think this is really mean to this particular music. That's roughly the quality you get from a phone. So they designed for this, which I think is pretty nice. Dropouts and stuff as well. Okay, so what they wanted to achieve was to find a particular offset in the song. So how many seconds from the start was this clip that we just sent there. Obviously, we still want to detect things, even if there is noise present, and even if there's all these problems that I just mentioned. And we don't really want to have false positives either, for obvious reasons, but also this is made more difficult by music that's quite similar, where the tracks are quite similar to each other, or where have remixes, things like that. Also, people copy stuff, so sometimes you have this case that some sort of clip that is in one song also appears in another one. That was kind of the requirements, I think. Oops.
I guess the author didn't like what techno.
No, he did not. I know some. I have some insights into his music taste from his examples. Okay, so basically we end up with these two requirements. It should be effective. We take a short, noisy sample, and we still want to have a good match. And it should be efficient because we have millions of songs in our library. I looked it up. Spotify is at like 40 million songs at this point. Or no, that was iTunes. Spotify is like 100, something like that. So we have hundreds of millions of songs that we potentially have to match here. All right, so now we go through the, I think it's 5 steps that the algorithm operates on. And, you know, because I'm stratifying this talk, I put a giant formula on it, which you should totally ignore. This is just, you know, for decoration. So the step 1, no, seriously. Why would you put this on the slide? I'm still mesmerized by this. Okay, I stole this from Wikipedia, by the way. So this is the first step. We do the fast Fourier transformation. It's a well-known signal processing step. I'll show an example in a bit. This has been optimized to death. There is highly efficient Fortran code for this. And what it basically does, it takes a signal, audio signal, and it turns it into a spectrogram. I will show what a spectrogram is in a bit. The conceptual translation is that we go from the signals all being mashed together in the time domain into separating them into their frequency. So basically you can think of the Fourier transformation as separating the individual frequencies out of a audio signal. And there's this algorithm there if you're interested. There's an E here.
MK in there.
Sorry?
There's even MK in there.
Okay.
MK.
Here, Martin. Have you been on Wikipedia again?
Substituting all the
I looked at
constants.
this structures even in the end of the 80s.
Yeah, it's ancient stuff. Yeah. It's one of the most important things in signal processing is the fast Fourier transformation.
Isn't it like written like the fast Fourier transform in the wild is written in Erlang and then compiled to C, right?
I don't know.
It's something really.
I have not looked at this. This is not my department. All right. I will show you how it works, and you will understand it works, and you don't have to think about it. I will show a demo how this works. So here we have Audacity, which is a audio editing tool. So I will generate a tone. Let's see. Sounds pretty good. 1000 hertz. And then I will make so we have 1000 hertz now, and then I'll make another one, and then another tone. Oh, let's do maybe 2000 hertz. Pretty good. Okay. And now in Audacity, it actually can do the FFT for you, and you can see that there's shockingly two peaks, one at 1000 hertz. And one at 2000 hertz, and that's basically what it does. It takes if I play the signal together, let me just do that. That's what it sounds like. This is the mixed signal, yeah, so it's like mashed together. But the FFT that you can see here is basically separating those two peaks out again, which you cannot see in the mixed signal. All right, this was the FFT demo. Yes?
Can you go back to the previous slide? There's a mention about the creator algorithm. Did you talk about it or what?
No, I'm just saying we use this. I'm not going to talk about it because it's signal processing and it's not relevant to this talk. Go look it up if you care.
Next time, okay.
Okay, so now what we can do is we can basically, for every time unit in the song, which is on the x-axis here, we can make one of these plots that I just showed in the Audacity program, and then we end up with this spectrogram. So basically, every sort of vertical line here is one of these curves that shows you the distribution over the various hertz spectrum. So this is hertz and this is time. And this is often plotted with colors, where basically a brighter color means a higher intensity and a darker color means a lower intensity. And this, in this case, is a Bob Dylan song, like a Rolling Stone. And if you squint and look at a lot of those, you know, as I have done, then you can kind of see that this is a typical pop song where you have the refrain, I don't know what you call this in English actually. The chorus. You can see the chorus, you know, for example, because it's this repetitive pattern that happens every now and then. So things like that. Obviously the nerds have gotten their hands on this. This is a song by Aphex Twin, which is a rather, let's say, innovative band. And they actually mix the music in such a way that the spectrogram produces this image, which I think is, respect. So
How
you
does
can.
this sound?
Huh?
How does this sound?
Oh yeah, I can.
White noise.
No. I'll play it. I'll play. No worries. We can play music. Also, this album picture is excellent.
Is it near the end of the picture?
Okay, no complaints yet.
It sounds a bit
the
odd.
picture is near the end, right?
Huh?
I thought the picture was near the end.
Yeah, I don't exactly know where it is, but it's somewhere in there. Could be. Who knows? Yeah. Anyways, this is why I was really excited about giving this talk, because it gives me an opportunity to mess around mercilessly. So, okay. All right. So now we have this. Basically, this is the first thing we do with our song. We generate this picture. Conceptually, think about that we just create this picture the spectrogram from the audio, and this is a pre-processing step, and it involves the FFT and not much else. And as I said, yes, you have to apply the FFT, but you don't necessarily have to understand how it works in order to get this picture. All right. This is again slides from our friend from Shazam. This is actually the spectrogram that is in the paper. I was very happy I found the color version somewhere, because the paper is only black and white. So basically we take the spectrogram, and the spectrogram has some nice properties that we like. The spectrogram is robust against noise, reverb, dynamics, some sort of other kind of distortion. If you run the same song through the spectrogram generator, you get exactly the same spectrogram again. Excellent. And it has been found, this is also one of the things that they describe in the paper, is that the spectrogram also tends to survive through very horrid compression algorithms, such as the ones that are used by the phone companies, right? So it will look slightly different, but if you think about it, like the general pattern will stay the same, no matter how terrible you treat it. And that's excellent, because we want to detect audio, right? So what we do basically is we take the spectrogram and we'll detect all peaks. And peaks are visible here with this red color, but in general what we do is we take a certain neighborhood size, and we take the highest sort of intensity as a peak. And when we do this with this picture, we end up with these peaks. So this is now this spectrogram where we have detected all the peaks. And now you could say, okay, fine, we will use the peaks to detect the song, because we can obviously match these peak patterns against the known music, and then we're happy. But it actually turns out that this is not precise enough. And this was extended. So we were not only taking the peaks, but we're going to take combinations of peaks, and that's kind of the key innovation of the paper, is to somehow connect those peaks in the time domain. How does that work? Well, what we do is we take any of those points. So this is an algorithm that really runs like for every point, this point in this example, generate all combinations with this point in a so-called target zone, which is just, again, it's a defined area relative to it in the spectrogram. So, but basically the target zone here would say, okay, you go 1 second to the right, and then everything within a 1000 hertz band for 1 to 3 seconds is your target zone, right? That would be the way how we select those combinations of points. And this is really interesting, because it kind of exploits the fact that if you play recorded music, there's really a strong correlation in time, right? Because we have a signal now, and the signal in 5 seconds is going to be whatever is in that music. And it's not going to be random, it's going to be whatever that song does, right? So basically for every point, again, we generate all these combinations with all the points in its respective target zone. So we end up with a lot of points. And what this does, it's basically just making this pattern of peaks more unique. It's more unique for this particular piece of music. Okay, and then we hash it. So now the trick is now we generate hashes from this, and this is what took me a bit, time to understand it. What really helped to look at some crappy implementations and improve them, and sort of understand how this works. So basically, what we do is we take for all the pairs of points with the target zone points, we generate this into a tuple. You can think of it as a 4 tuple here. So we have a frequency 1, frequency 2, the time difference between the two, and the time offset, which is something we need later, so you don't have to care so much at this point. So basically, if we look at, let me just draw this because I want to use this later again. So again, we have the spectrogram, right? And we have a point here, and we have a point here. So then we have a time difference between the two. And we have a frequency 1, and we have a frequency 2. And these are the things that are basically concatenated and hashed. That's really all there is to it. We take these 3 numbers. Those are numbers, obviously, in the spectrogram we get the frequencies and the time difference we can compute. And we hash it. And that we do actually both. We have exactly the same treatment for the library data, so the known songs, and the clips that we want to detect. Only that, of course, in the case of the library songs, we know which song it is, and the clip we don't. So we hash those. Sorry?
So these time differences, are those absolute?
No, relative.
No, but I mean, because you said
in seconds.
The song could be played faster or slower.
That's,
bit, right?
Yeah, but that's actually one thing that is not particularly okay. You can work around this a bit by making this a bit more coarse, the time measurement, but that's actually quite sensitive.
That would actually also have an impact on the frequency.
Yeah.
If you play it slower, you will have.
So fast and slow is really problematic. Luckily, we don't have this a lot anymore because we have.
Well, what you do have,
all the time.
Right.
what you do have, especially in classical music, is transposition.
Right.
So playing it at a different frequency.
Yeah, I mean
recordings and not
but it's
Well, okay.
it's about playbacks of. But I mean,
If it's recordings, yeah.
for electronic music, it's actually still happening all the time that you would play back at a different speed because that's how you mix tracks.
Yeah. No, you can, of course,
and it works there, so I can tell this.
No, there's also some pre-processing you could imagine, like normalizing those a bit, but
yeah, fair enough. Yeah.
But the point is that we get a hash out of this. So we hash these first 3 entries here, and then we store that in a database with the song identifier, basically. Obviously, there's a big amount of parameters that we can consider for this. For example, as I said, in the second step, we detect these peaks for the constellation map. So of course, what constitutes a peak is a bit, you have in this case, they have a parameter for the amplitude limit and neighborhood size, so how many points around you're looking at that you can configure. The window size for the target area, the fan angle. The fan angle is the maximum angle of these pairs of points. You have then limits, of course, on the time delta, so the maximum limit on the time between two of these peaks, and then obviously from a performance perspective, you also might want to think about how big your hash should actually be. You can of course use the full amount of entropy that you have there, or you can shorten it, in which case you get collisions, but you might want to do that to reduce the amount of memory that you have to use. Okay. So the result of step 2 is a data set that looks like this. We have a table, song ID, hash, and offset. I will come back to the offset later. And what I in the software that I worked with, this came up to about 100,000 hashes per song being generated, which is quite a lot. If you imagine that you have 100 million songs, then times 100,000. But luckily these are hashes, and we know very well how to work with hashes, because we can, for example, distribute them pretty nice by doing range partitioning, for example. So this is not a problem in a sort of data management way. It's just that yeah, we're gonna look at those hashes again later. So yeah, but now we have done that. So now we have spent the time to crunch all the music that we have through this hash generator once, and we've stored that in our database, and that's great. So I have a SQLite file here on my computer with 500 or so songs in it. I'm going to use that later in a demo, but basically now we have that. And now we want to search. Well, we do, as I said, we do exactly the same thing again. We take the snippet, so that is whatever was recorded, and we're going to search the library. But this is actually not complicated. So I put the query that is actually run there here. So basically what we now do is we query the fingerprints, and then we search for hash in the long list of hashes that we generated from the snippet. Right, so from the snippet we get a bunch of hashes, in the database we have a bunch of hashes, and now the query that the lookup that we have to run is simply give me all the entries from the database of known songs where the hash matches any of these large lists of hashes. And it's actually quite, it's like a many point query where you have to rewrite into a join, because you will also from a short snippet end up with thousands and thousands of hash candidates, right? And it's very likely that there will always be some matches, because some of them are just random. We are going to look at, in this step 3, we're going to look at how we actually find out whether, how to rank those matches and to find out which is the best one. Is that step 4 already? Oh no, step 3 was finding the candidates, and step 4 is the ranking. Okay, so this the trick that you do to match those is you plot the time of the sample against the time of the library database, basically for the matching hashes. So those are all matching hashes, and then you just put the time that the match came from in the snippet versus the time the match came from the database against each other. Right? You do that for every candidate sort of song from the database. And in this case, this is not a match, right? You can see that these scatter plot here is all over the place, and it's not matching. But because what you would expect if the snippet and the database entry actually were from the same song, is you get this sort of diagonal list of matches, because obviously the time is correlated in both cases, and if something matches, then yes, this will be somewhere in the song, but the general progression of the time offset, both from the database sound file and from the sample, will sort of progress together along the matches. That's kind of because they are both the same. The matches should line up. And again, there will be some noise, but that's fine. So basically, what we now need to do is we have these lists of matches with candidates, and we want to find the one with the most diagonal sort of pattern in the scatter plot. And in the paper they talk about, this is actually what I like, something I like about the paper. In the paper they say, yes, and the textbooks would tell us we now should do this and this transform, and then we would have a way of detecting this. But then they say, yeah, never mind. Just subtract the time offset sort and look to a plateau search, and it's fine. And that's actually exactly what happens. So basically, what you do is, you subtract those offsets from each other for all the matching hashes. So basically, we have the match, we have the hash and the time offset from the library, and we have the snippet, and we have the hash and the time offset, and basically we say just T1 minus T2, and then we do a plateau search on this. After sorting, we do plateau search on these time differences, and they should be constant. The one with the most amount of constant time differences wins. Yes?
Is there any kind of special trick that you would need if you want to do this continuously? Because you assume now that you have a set from your listening sample, but Shazam does it like while it's listening, so
Yeah.
you would have continuously updated.
I don't think it's particularly complicated. I mean, yeah, you have to update the matches, you have to find new matches, but you keep the ones you have,
And they just have a confidence
and you drop the
threshold.
drop the ones that are too old. I don't know.
Because Shazam sometimes listens for a long time and sometimes for
Yeah.
a short time. So.
Yeah, I think it has a feedback that tells it to continue listening. So if it immediately finds a good match, it just early aborts. You know, it says, it's this song.
Mhm.
If anybody wants to have a look at this thing, I forked a broken guitar brepo and I made it work. So I'm gonna show that next for a little bit. So demo. Obviously, first let me show you the database. So this is a SQLite database, of course. So here, as you might expect, we have some songs and some fingerprints. So if you look at the songs, then we have, this, as you would expect, you have a Rolling Stones song name, and you have, I'm not exactly sure what that is for, but the interesting thing is here the ID, the primary key if you want. And then we can look at the fingerprints. How many do I have? So yeah, indeed, and here's the hash, and we have a mapping to the song, and the time offset that hash was in the original. Constant SQLite is not trivial because they need to check whether there's any rows have been deleted. They have these gravestone markers. What do you call this?
And you can just merge them.
Ghost dragons or phantom? No.
Deleted ones. I don't know.
Tombstones.
Thank you.
They can just merge the accounts, like just passion of one.
This is a B tree. It's a B tree. Anyways, and they don't know how big it is actually. So here in this database we have 71 million hashes, which is I think quite extensive for SQLite. It's quite interesting because the GitHub repo had two implementations for the database, one using MongoDB and one using SQLite. And they said, oh yeah, if you have more than 10 songs, you should really use MongoDB. I thought, bullshit. So I looked at the schema and they failed to actually use the hash as a key. In which case every single loopback is a full scan of the database. And then indeed you need MongoDB to fix this problem. I totally agree with this choice of technology. Anyways, it's fixed now. Actually, this is a good case for SQLite's index tables.
Right?
No, index tables, where you have tables that where the row ID is actually a column of your data, and then you have a very nice B-tree lookup without additional indexing. All right, so demo, so this is the database, and now we have a bunch of Python scripts here that actually query this, and I'm going to show you some examples. So I have made some samples here. So here is a clip that sounds wonderful. Wonderful music. Okay, so if I now throw this clip into this wonderful script here, then it will basically generate the hashes, run the queries on the database, and then do the ranking as I've explained, and it will tell you, okay, this is this song, Acoustic Alchemy, I don't know this song. And it tells you here, as you can see, that this is 110 seconds into the song, and the confidence is 2,292, which is pretty high. So I thought, let's now try to break it. What do I have to do to this music for the detection to not work anymore? So first thing I tried is to add noise. So I'm sorry for your ears, there will be more noise in the coming minutes. So this is a 10% noise added here. So if I run this through the detection, you can see that the confidence dropped down a bit, but it had no issues to pin it down to the same song. Now this is actually, that impressed me a lot, because if I take a 50% noise, again my apologies, this is quite a lot of noise. You would agree with this, right? And this is like serious bar noise there.
But does the white noise get any kind of frequency peaks?
Yeah, of course, it's randomly.
It's white. I mean, it's,
Yeah, it does. But it's still amazingly, with this 50% noise, finds the correct song, although with a very low confidence, and I think 60% didn't work anymore.
No, but on the spectrogram, you wouldn't really see the fine peaks with white noise, right? It will be like a well-distributed intensity over the whole frequency range, so you won't actually get peaks from white noise.
But
I would say.
I mean, you will get randomly some. It depends on
Yeah, I mean, if
threshold.
you make the
right?
if the resolution is very high in
Yeah.
time, then yeah, you would see peaks. But I wonder if the spectrogram is actually that high of a resolution.
Yeah, but it doesn't
Depends on
fuck
the
with the rest, of course. All the FFT will have more
Yeah, but
problems.
if you're really just looking at peaks, then the peaks should really survive well with noise.
Yeah.
So I wonder if noise is the hardest thing for it.
No, it's not. No, it does very well with noise.
Yeah,
I'm not
that-
done yet.
Exactly.
That's the point.
Noise is no problem. Yes.
Yeah.
Okay. So then, but what you would expect is, because the thing is actually quite dependent on the time difference, because that's directly going into the hash. So you would expect, as soon as you mess with either the time difference or the frequencies in the music itself, you would get a problem. So if here I have a clip, so this is now just a 1%, I think, pitch increase, and if I run this to the or was it 10? I think maybe a 10% pitch actually. Oh no, here the 1%. There it is. So if I run this through the shredder, then I don't think it's gonna find it. Or maybe it does. No, it didn't. It found something else, which is exactly what you would expect from if you have a hash on these things like frequency and time, and you mess with the frequency all the time, then it breaks down instantly. Obviously, as I said before, you could imagine defending against this by, for example, discretizing the signal before you generated the hash. So you could go into frequency sort of slots, and you could compress the time bit more into slots, and then you have a much better chance of this still finding a match. But this is of course the weakness. But it's also interesting that in a typical playback situation without vinyl, it actually is very likely to work well, because it can deal with this noise, which is the most problematic thing actually in this environment. So that was kind of the algorithm. Are there any questions at this point?
So now the next step, use it in a different setting.
What? You mean the concrete?
Yeah.
Yes, we will get to this. Hello. So you missed the wonderful white noise that I've treated these people with today. But there's one more thing actually. So I have a bit of a goodie for you, because obviously I have too much time on my hands, and as you know, so here's the spectrogram from the paper, right? This is what you looked at, and this is used for all the examples and so on and so forth. And I looked at this and I thought, which song is that? Because I mean, it doesn't say anywhere in the paper. I googled around extensively in the slides and everything. It doesn't say anywhere. So it's like, But the spectrogram is a representation of the music in the time domain with all the frequencies separated out. So maybe this process can be reversed, and maybe the algorithm is so good that it can actually survive being printed in a fucking paper.
Yeah. It looks like a solo piano piece.
So I shall demonstrate how this can be done. So there is this, no, this is my photos. This is not the correct one. Photo sounder, yeah. So there's this program that I found. And what we can do now is we can actually load the picture from the paper. This is just a screenshot. And this is really, paper, PDF, download from the internet, screenshot, and so on. This is, and then, no bueno. However, if we invert, it starts getting like somewhere, Okay. So I mean, obviously I had to learn how to operate this program. So then if we look at the paper again, we can see that down here, you can't really see that in the back, but there's a time domain, and thankfully there's actual seconds there. I mean, I guessed these were seconds. And here we have a frequency, and these are absolute numbers as well. So in this wonderful program here, you can actually configure. So first we do the frequency scale to, come on, linear. Yeah, first we do the frequency scale to linear. Then we can configure the pixel per second resolution to match up with the, I believe, and if you look carefully, you can actually see the tick marks from the screenshots here in the bottom. Yeah. So we can match this up with the 12, was it? Here, that's about right. And then the max frequency was 3,500 on the top tick mark. So we don't want all these kilohertzes, we want 3,500. And I got this. And I thought, I don't know, this doesn't sound like music anyone could like. But I was mistaken. So if I go back to my Shazam, let me try. I have prepared like a backup in case this doesn't work live now, but we'll try it here. We'll try it live. So we'll go back here. I'll click my button. Yes, and play. I'm sorry about that. However, this is not a problem because I have played with this extensively, and I have a file I generated from this that sounds slightly different. But you can see how it's a similar thing, right? And amazingly, it did survive. Why does it now play the? Shut up. Okay. Amazingly, this is something that really, when I was really sold on this algorithm, if you imagine the amount of things that has happened here for this thing to work, basically, it's so good that you can print your music in a scientific publication and will still be able to be correctly detected. So that was it for today.
Well,
thank you.
Did you confirm with the authors that this is indeed the plot?
I should email them and be like, I know your secret. No, I'm very sure. Actually, I can prove it to you. Wait a second. So this is what we have recorded. This is what I read from the photo reverse thing, right? Okay. So that's good. And now if I actually have the thing here, and I have looked up where the thing is. 1 second. 2min46. 2min40.
This is so large. Oh,
Huh?
take 5, sorry.
That's the song, yeah. So it is that one. I'm sure. I'm quite sure. Yeah. But I thought it was quite funny that it was possible.
Okay.
Yeah. And if anybody wants to look at the Python stuff.
Thank you, Hannes.